Okay, everybody, so in this video we're going to start talking about some other data structures we can start to form with just some of the basic knowledge we've already learned so far. And one of the first data structures we're going to talk about is basically the idea of a stack data structure. I know some of you have probably covered this in 250, or you have covered it in your 250 class, but we're just going to take another refresher and see how it all goes. Okay, so the whole idea of creating these other data structures is the fact that sometimes just storing data in a plain linked list or a plain array just isn't enough. Sometimes we want to access data in certain ways, and just having a plain linked list isn't really going to enforce that specific behavior for us, right? When we just have a plain linked list, we can start at the beginning of the list and visit every node in the list, but sometimes we don't necessarily always want to do that, right? What if we want to apply certain rules to how we access that specific data that we are storing? So for instance, say we only want to see the last element that was put into the list, or we want to see the very first element that was put into the list, right? We can apply certain rules and thus form different data structures that enforce those rules for us. Okay, so the stack, or the idea of a stack, is one certain way to enforce rules on how we access a data in a general linked list or in a array, for instance. Okay, a stack is going to exhibit what's known as first in, last out behavior, FILO. So basically, in a nutshell, the first element that's put into the list is always going to be the last element that comes out of the list. Okay, and we will write certain functions that are going to enforce that for us. Okay, so if you want the best general idea to think of a stack, uh, this is kind of the tried and true method. This is, how it was described to me when I started out, is basically think of any buffet restaurant you go to and think of the stack of plates that you find at the front of the buffet area, right? So they're always upside down, and whenever someone puts more plates onto that stack, whatever plates that were there before get pushed down lower, right? So they would be the last plates to come out, even though they were the first ones to be put on the stack. As more and more things get added on top and and further on top, right? All of those older plates keep getting pushed down farther and farther and won't actually come out or be able to be pulled out of the stack until all of the newer plates have been taken off first. Okay, right? It just simply pushes the older plates down. Right, so that's going to be the same idea we're dealing with in our stack data structure. Right, the oldest data is going to get pushed farther and farther down as newer data gets put on top and is accessed earlier. Okay, uh, basically, with a stack, we're expected to be able to store, any arbitrary amount of information, so zero things up to 100,000, million, what have you. And the other stipulation and rule we have is that on a stack, we can only access the top element. Okay, there's no reaching below the top element. We don't see what's in the middle of the stack. We don't see what's at the bottom of the stack. We can only get to what's on the top. And if we want to access some other elements that are below it, that means we need to physically remove that top element, and then the next top element, and the next top element, until we reach the data element that we're looking for. Okay, as you proceed through your computer science career, you're going to see that the stack and different forms of the stack play a very important role in computer architecture as a whole. You're going to hear me talking about, we allocate things on the memory stack, right? The program stack. Okay, that's not necessarily the stack we're dealing with, but the underlying computer architecture and how we call functions and how things are allocated in our computer memory is basically based off of this whole stack idea. Right, and once you get more and deeper into OS level things, you're going to see the stack behavior pretty much everywhere. Okay, so a stack, or when we're describing a stack, is going to have basically a set of 4 functions that we can use to interact with the data. Okay, basically we have the push function, which basically just says, okay, put something new on top of the stack. We are going to push this value onto our stack, right? And that adds it to the top, and then if we call push again, another thing gets put on top of the last thing we put on, and so on and so forth. Okay, the next element we have is the pop element. And pop is going to remove the top element from the stack, right? Okay, pop does not necessarily access the value. Pop just removes the value. Okay, to access the value that is at the top of the stack, we have a function that's just called top, right? And that returns whatever value is on top of the stack. It won't modify the value, it won't remove the value, but it will just give us whatever is at the top. Okay, and then the empty function checks to see if the stack is empty. Okay, now it's important to note that when we write our code and deal with anything that is a stack, it is very important to use this terminology, this push, pop, top, empty, right? We must use this terminology when we're talking about a stack, right? We're not going to call a function called remove or a function called add or append or anything like that when we're dealing with a stack data structure. We have to use the terminology push, pop, top, empty, etc. when we're dealing with these data structures. And the importance, we'll get to that importance in a little later video here, but right now I'm just going to introduce this whole idea of this specific data structure. Okay, so if we wanted to visualize a stack, right, we're going to have a couple different things that we need to keep track of. The most important one being we need to keep track of what is the top of the stack. So if we're going to just completely picture this, so right now we have basically an empty stack, right? And top is pointing to nothing. Right, so if we go ahead and say push 1 onto the stack, we add a 1, whatever that, however it's represented, in our program, and top now points at 1. And that is because 1 is the top element of the stack. Right? It is the top. Even though there's only one element in the stack, it is still the top element. Now, if we go ahead and we push 2 onto our stack, we see 2 gets put on top of 1, and top now points at 2. Right? And right now, we would have no way of accessing 1 unless we first remove 2 from the stack. Right? Then we could go ahead and push 3 onto the stack. We could go ahead and push 4 onto the stack. And we can see that everything is just growing in this up manner, right? Right, our stack is growing up. After that, we could call top, and that would just output 4 to our screen, right? Because 4 is the top element of the stack. Again, it's not removing anything, it's not modifying anything, it's just telling us what is the top of the stack. After that, we could start popping elements off. Notice we called pop, and 4 disappeared at our stack. After 4 was removed from the stack, we had to then tell basically what is our new top element of the stack, and that is 3, right? Because we removed the top, the next element underneath 4 becomes the new top. Again, we could call top. It would output 3 because top is pointing at box 3. We could again call pop, which would remove 3 and make 2 our new top of the stack. And then after that, we could go ahead and start pushing more values back on the stack if we wanted to. Right, so here we went and we pushed 20 back on the stack. Right, so it again went on top of 2 and became our new top. Okay. After that, you could again go pop and pop until our stack is empty. And there's nothing more we can do with it until we would add more elements back onto the stack. Okay, because this whole idea of a stack is kind of this general idea of how we handle data, right? There's no per se right or wrong way to implement our stack. We just need to pick an implementation that follows these rules, right? The whole rules of first in, last out behavior, which I need to change that. Got my wrong letters in there. Let's just change that real quick. First in, last out. Okay, so as long as however you implement the stack, as long as you follow that behavior, your stack is technically correct and adhering to the stack behavior. Okay, though you might find some implementations are a little more efficient than others. So the two main ways that we can represent a stack is basically by making use of our arrays or by making use of a linked list and just simply applying our rules to those basic data structures. Okay, so first we'll just go ahead quick talk about our array-based stack. So let's say we are using an array. So with an array, we will basically be able to store a set number of elements, right? Because an array is a fixed size. So if we know the maximum possible number of elements that will be in our stack at one time, this could be, a pretty good choice. Okay, but when we choose our array to represent our linked list, we basically have to make some design decisions. The primary one basically being which end of the array is going to be the quote-unquote top of our stack. Okay, and this choice is really going to affect performance and affect how our stack is going to operate. Okay, so let's say, for instance, that we have this array right here, and we're going to use that to represent our stack. And we're going to say index 0 is always going to be the top element of our stack. Okay, and we're going to use this next variable down here just to say where the next element should get put, more or less. It won't have that big of a part to play in this actual representation. Okay, so let's say we go ahead and we push 1 onto our stack. Okay, so we push 1 at index 0, right? Because index 0 always represents the top of our stack. Now, let's say we need to push 2 onto our stack. Okay, remember, when we push 2 onto our stack, it has to become the new top, right? So in order to get 2 into index 0, we first need to take 1 and shift it down 1 element into index 1, and then we can put 2 into index 0, right, to keep our stack behavior. If we decide we want to push another number onto our stack, that means we need to take 1, move it down to index 2, and take 2 and move it down to index 1 in order to make room so that we can actually put 3 into index 0. And if you notice, as our stack gets bigger and bigger and we push more and more things onto our stack, we're going to need to shift more and more times, right? So if we push a new element on, we need to shift each element that's already in our stack to the right by 1, right? So if we have a really big stack, as our stack gets larger, our whole operation is going to get slower and slower because it's going to take more and more time to shift each single element in our stack to the right in our array by 1, right? And as you can see here, we started off by having to shift 1, then we had to shift 2, now we're shifting 3, next time we'll shift 4, etc., etc., etc. So it could be that this might not be the best decision, right? And the same is going to hold true for if we pop something off the stack, right? So if we pop 4, no, I guess it was 25. If we pop 25 off the stack, now we have an empty index 0. And in order to say what the new top is, we are going to have to shift every element that was already in the stack back to the left by 1. Right? So we're paying a pretty good hit, performance hit, on every single push and every single pop operation, just because of all of the shifting back and forth, left and right, that we're going to have to do in order to maintain our stack behavior. All right, so if we keep popping, we just have to keep shifting, right? So with all of that said, having our top specifically stated at index 0 might not be the best option, just because of all the shuffling we need to do every time we would add or remove something. So instead of having our top at index 0, what if we say our top is always the rightmost element in our array, right? This is going to force us to keep track of a little bit more information, but it might have some pretty good benefits in the long run. Okay, so now instead of saying index 0 is always the top of the stack, now we're going to keep track of a variable that's going to tell us where the top index is. So right now the stack is empty, and our top index is going to be 0. Okay, so if we push 1, notice 1 went into index 0 and we incremented top. Okay, now this is going to be a design decision moment as well. This one won't really affect performance as much as just your overall thinking of how your stack should work. Okay, so our basic question is, do we increment our top variable before we add the number to the stack or after we add the number to the stack? Right, so this will determine whether when we need to access our top of the stack, do we need to subtract 1 from our quote-unquote top, or can we just take the top element? Okay, I opted to basically increment our top variable after the new number is pushed on the stack, right? So right now, we have one number in the stack, and we're basically saying the next top, or where our next number is going to go, is going to be index 1. Right? So if I called top right now, I would basically take this variable and subtract 1 from it to get our actual real top of the stack, not where the next top is going to be. Okay, so again, if we push 2, notice 2 went into index 1, and we're saying that our new next top or next variable is going to go into index 2. Okay, if we push 3, 3 went into index 2, we incremented top, so top is now at index 3. We push 25, 25 went into index 3, and we incremented top, so it's now saying index 4 will be the next element we will use. Okay, now if we call top, we basically take whatever our variable is at, subtract 1 from it, and that will give us our top of our stack, right? So now we have 25 at index 3, and we print it out. Okay, if we call pop, all we need to do is basically subtract 1 from our top variable, right? So we don't really remove the number from the array. We just say, we just subtract 1 from where the top of our stack is, so that that index could potentially get reused to store another number. Right, so if we would call top now, we would take 3 minus 1 to get 2, and we would print out 3 because that is our current top of the stack, which we just did there. Okay, if we call pop again, we subtract 1 from our top variable, which means that this index could now be rewritten by something else. Right, so if we called push on 76, we would overwrite our 3 with 76 and re-increment our top variable. And if we would call push 89, then we would overwrite that number, just because that is what our top variable, or where our top variable told us to actually stick that number. Okay, so again, arrays are, can be a very good option to implement our stacks with. However, just because of how arrays are allocated, they have a fixed size, right? So they may only be necessarily a good choice when we know what the maximum stack size may be at any given time. When we don't know how big it may be, that's when a linked list may be a better option. And of course, linked lists have more overhead, but that extra overhead makes them a more flexible data structure. Okay, so the only thing we're going to really need with our linked list is basically we'll have a normal linked list, but then we will have a special pointer that if essentially points to the top of the stack. Okay, then when we're thinking about hooking up our linked list and using it for a stack, we need to make another decision, and that basic decision is, okay, how do we link all of these things together? Do we say top points to the top element, which points to the next element, which points to the next element? Or do we reverse that and say, okay, top is pointing at the top element, but when we add something, we just add it at the bottom? Okay, that's the design choice we need to make. And again, that's going to affect the overall efficiency of our algorithm or of our data structure. Okay, so I'm going to opt to use this method right here, where top points to the top, and then the top element points to the next element, which points to the next element, and keeps digging further down and down. If we were to use this representation over here, we would then need a second pointer pointing to effectively the bottom of the stack, and then whenever we added something new to the stack, we would have to walk all the way up and add it and stuff like that. Okay, so we're starting off from an empty linked list. We push 1, so top is pointing at 1, and everything's happy. If we push 2, right, we effectively 2 will point at the old top of the stack, and then top points at 2. Okay. If we push 3, 3 effectively points at the old top, and then top points at our new element. Right? And this process is going to continue on over and over and over again. Okay, if we push 25 on the stack, 25 is effectively pointing at the old top, and then top points at our new element. Right? And then it's the exact same behavior that we saw before. If we pop an element off, notice we remove 25 from the stack. If we call pop again, we remove 3. If we call pop after that, we would remove 2, and then 1, and so on and so forth. Okay, now the pushing and popping we're doing should actually look pretty familiar to something that we've already done in the class. Okay, if you don't necessarily see it from just looking at this diagram, try taking this diagram and basically laying it on its side. So it's more, instead of looking like this stack, we see it like a just normal linked list would be. Okay, and if you want to sit and try to think about what this looks like, take a minute, pause the video, and think about, what does this push and pop operation actually look like, and what are they that we've already done. Okay, so effectively, a push is precisely a list prepend. We're pushing an element on the front of our list. Top is more or less our front pointer, which holds on to our list, and push just adds something new to the front of that list. And a pop is precisely a remove front of that list. Right? So we've already done these operations with our normal linked lists. Right? Assignment 1. That's basically what you guys did. You wrote up a linked list that did remove front, remove back, add the front, add the back, and search, etc. Okay, a push and a pop is basically the exact same thing, just with a different name attached to it, right? And remember, we have to use those different names because we're now using them in the context of a specific behavior, right? If we actually reversed how our linked list was hooked together, basically, instead of a push being more or less a prepend, push would effectively be an list append, and a pop would effectively be a list remove back or cut, whatever you want to call it. Okay, so these decisions we're making as we design our data structures, just as simply as, okay, which end of our array is our top of our stack, How are we going to link together our linked list when we design our stack? All of these things are design decisions that will, in one way or another, make a difference in the efficiency of our algorithms. Okay, so these are all things you need to keep in mind, especially because little decisions like this can really affect the efficiency of our data structures, especially once we start feeding it very, very, very large data sets. Okay, so kind of think about that a little bit. There's going to be example code on D2L for stacks. I would recommend playing with that code a little bit. And in the next video, we're going to go ahead and quickly write up just an array-based stack, just so everyone can kind of get a feel for the behavior and mess with it a little bit. And then you can go ahead and take the linked list base code that I will give you and mess with that and make sure you understand it as well. But that is all for now, and we will see you in the next video.